Oh, it's an induction question. It says use the definition, so we expect to use that somewhere through it, but the proof we have to do is that this is equal to this for all positive integer n's. So let's do examine n equals 1. The sum from r equals 1 to 1 of rc1. Well, that's going to mean I'll take the first up to the first, that's the first one, put 1 in for there, that's 1c1, which looking at this is going to be 1 up there is 1 factorial over r is 1 factorial and subtract r is 0 factorial, that's 1 over 1, which is 1. Let's check the other side. So n plus 1c2 equals 2c2, which is 2 factorial over 2 factorial 0 factorial, which is also 2 over 2, which is 1. So therefore true for n equals 1. Now let's check or examine. Oh no, first of all, let's assume it's true. Let's define it first, because we might define this p of n equals the sum from r equals 1 to n of rc1. Assume p of n is true for n equals k, and then examine p of k. So this says therefore that the sum from r equals 1 to k of kc1 equals k plus 1c2. Examine p of k. P of k plus 1, actually what to do. P of k plus 1, which is the same as p of k plus, because when we do this, p of k plus 1, we're going from 1 to k plus 1. Actually, when we write that, that might work better to see it better. That's equal to the sum of r equals 1 to k plus 1 of k c1, which is the same as the sum from r equals 1 to k. That's the first k terms. So it should be k, it should be r. This one should be r as well. Of rc1 plus the k plus 1 term, which is k plus 1 c1. And if we look, we've assumed this is true, which means that this equals this. So I can replace that with k plus 1 c2 plus k plus 1 c1. And let's go back again and see, we should be able to use this bit here to work out what that is. So that is k plus 1 factorial over r is 2 factorial and k plus 1 subtract 2 factorial plus k plus 1 factorial over 1 factorial, k plus 1 subtract 1 factorial. Let's use the definition. Let's just simplify that. This becomes k subtract 1 factorial. This becomes k, let's put 1 factorial in there as anyway, k factorial. To add these two fractions, I need a common denominator. So the common denominator will get a 2 factorial, so I need to multiply this by 2 numerator denominator. And to make this a k factorial, this is k subtract 1 times k subtract 2 times k subtract 3 dot 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 down to 1. And k factorial is k times k subtract 1, k subtract 2, k subtract 3 down to 1. So actually to get from this one to this one, it's getting from here to here, I need to multiply by k. So that gives us a numerator denominator multiplied by k over 2 factorial. k factorial plus multiply numerator denominator by 2 over 2 factorial k factorial. We now have a common denominator. And in fact, there's a common factor on both of these. So we get k plus 2, k plus 1 factorial over 2 factorial k factorial. If we look at this, k plus 1 factorial is k plus 1, k plus 1, k down to 1. You put a k plus 2 on the front, that becomes k plus 2 factorial over 2 factorial k factorial, which actually is the same as, so I should have a bracket there, double brackets, k plus 1 factorial over 2 factorial, and this is k plus 1 subtract 1 factorial, no, k plus 2, sorry, subtract 2 factorial. And if we look carefully at our formula up here, that's k plus 2, and that's k plus 2 subtract 2, and that's 2. That means it's k plus 2, 2, which equals k plus 1 c 2. Which is exactly what we're looking for here. We wanted the same thing we had there with a k plus 2 there, or k plus 1, and our 2 there. Hence, by induction, true for all k. K is the set of positive integers.